book nibbles. Big ideas, small bites. Michio Kaku's Hyperspace is at once a sweeping history of physics, a visionary map of possible futures, and a meditation on the human imagination. The book opens with a kind of mental exercise that Kaku returns to throughout the narrative. Imagine creatures that live in a world of only two dimensions, a flat sheet where the idea of up and down is inconceivable. These flatlanders, to borrow Edwin Abbott's 19th century metaphor, cannot conceive of a third dimension any more than most of us can genuinely imagine a fourth or 10th. Kaku invites us into this analogy not just as a playful thought experiment but as a serious tool. Just as two-dimensional beings might find our three-dimensional existence mysterious, miraculous, and even divine, so too could our own universe be just a shadow of higher-dimensional realities. And from there, he begins an odyssey that takes us through Newton and Einstein, wormholes and time travel, and finally into the frontier of string theory, which suggests that the ultimate laws of nature may be written not in 3 spatial dimensions but in 10. The story of hyperspace begins with history, because Kaku emphasizes that scientific revolutions often begin with shifts in how we picture space itself. In the Newtonian worldview, space and time were a rigid stage, a backdrop against which planets and stars moved under the influence of gravity. Newton's great triumph was to unify the heavens and the earth with a single law, explaining both falling apples and orbiting moons with the same mathematic. But even as Newton gave us a vision of a clockwork universe, he left behind a mystery: what was gravity itself? He could describe how masses attracted one another, but the mechanism remained obscure. Newton himself admitted as much, saying he would frame no hypotheses about the cause of this invisible force. Space was absolute, a fixed arena, and time ticked uniformly for all observers. That certainty began to crack in the 19th century as new discoveries in electromagnetism revealed that forces could be transmitted through fields that permeated space. The work of Faraday and Maxwell introduced a different kind of unity, one where electricity and magnetism were two aspects of the same phenomenon. Maxwell's equations showed that light itself was an electromagnetic wave, traveling at a fixed speed, and here the seeds of Einstein's revolution were planted. If light always moved at the same velocity, regardless of the observer's motion, then the Newtonian framework of absolute space and time could not hold. Einstein's special relativity replaced those absolutes with a single fabric of spacetime, where measurements of length and duration depended on the observer. The famous equation E equals mc squared fell out of this new vision, showing that matter and energy were convertible. Einstein went further with general relativity, recasting gravity not as a force acting at a distance but as the warping of spacetime itself. Planets orbit stars not because they are pulled, but because they follow curves in a four-dimensional landscape bent by mass and energy. Kaku emphasizes that this was the first real introduction of hyperspace into physics, because Einstein's general relativity was most naturally expressed in terms of higher dimensions. Mathematicians like Riemann had already developed the tools to describe spaces of any number of dimensions, but Einstein's use of 4, 3 of space and 1 of time, demonstrated that the mathematics could map onto physical reality. Yet even this was not the final stop, for general relativity resisted unification with quantum mechanics. Physicists sought a theory of everything that would reconcile the physics of the very large with the physics of the very small, and again the road seemed to point toward higher dimensions. One of the most compelling sections of Kaku's narrative is his discussion of Theodore Kaluza, a mathematician who in 1919 proposed an audacious idea: what if we added a fifth dimension to Einstein's equations? To the astonishment of those who studied it, Kaluza's mathematics seemed to unify gravity with electromagnetism in a single framework. The idea was radical but elegant. The equations of general relativity, when extended to 5 dimensions, contained Maxwell's equations as a natural byproduct. In other words, electromagnetism could be interpreted as the curvature of the extra dimension. This was the first serious attempt at a higher dimensional unification, a glimpse of the power of hyperspace theories. Later, Oscar Klein added the suggestion that the fifth dimension might be curled up, compactified so small that it was invisible to ordinary perception, much as a tight cylinder looks like a line from far away. The Kaluza-Klein theory was a promising step, but it languished for decades, overshadowed by the rise of quantum mechanics and particle physics. Still, it planted a seed that would later flourish in string theory. Kaku weaves these technical ideas with vivid analogies. He asks us to picture ants crawling along a garden hose. To the ants, the hose seems one-dimensional, just a long line. But from our perspective, we see the second dimension of the hose, the circular cross-section. The extra dimension is real but hidden from the ant's scale of experience. In the same way, Kaluza and Klein suggested, our universe could contain extra dimensions that are wrapped up so tightly we cannot detect them. The hose analogy recurs throughout the book as a metaphor for compactification and the limits of human intuition. Having established the conceptual groundwork, Kaku then guides us into the modern age of physics, where attempts to unify the forces of nature lead inexorably to hyperspace. In the standard model of particle physics, the zoo of subatomic particles, quarks, leptons, bosons, interact through four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. By the late 20th century, physicists had successfully unified electromagnetism with the weak force into the electroweak theory, and the strong force was described by quantum chromodynamics. But gravity remained stubbornly outside the picture. The dream of a single theory explaining all forces, the so-called grand unified theory, seemed out of reach unless gravity could be brought into the fold. Here is where hyperspace re-enters the story, because string theory, one of the most promising candidates for unification, requires extra dimensions to be mathematically consistent. In string theory, the fundamental building blocks of reality are not point particles but tiny vibrating strings of energy. The different modes of vibration correspond to different particles, much as different notes on a violin string correspond to different sounds. The mathematics of string theory, however, only works if space has more than 3 dimensions. Depending on the version, the theory requires 10 or even 11 dimensions. This sounds fantastical, but the logic is compelling. Without those extra dimensions, the equations collapse. So if string theory is right, then our universe must contain unseen dimensions, perhaps compactified like Kaluza and Klein suggested. Kaku delights in explaining this not as science fiction but as a serious possibility emerging from cutting-edge physics. The implications are staggering. Higher dimensions may not only unify the forces but also offer solutions to some of the deepest puzzles in cosmology. Black holes, for example, can be reinterpreted through the lens of higher dimensional geometry. Wormholes, speculative tunnels through spacetime, become plausible pathways for travel across the galaxy or even between universes. Time travel, usually confined to the realm of fiction, emerges as a theoretical possibility within certain solutions of general relativity. Kaku explains the difference between closed time-like curves, which allow a return to the past, and the various paradoxes they entail. He does not overstate. He makes clear that practical time travel may forever remain beyond our reach, but he emphasizes that physics no longer rules it out. In higher dimensional space, shortcuts that appear impossible in 3 dimensions may be entirely natural. The book also ventures into the cosmic scale, considering the origin and fate of the universe. Kaku describes how the Big Bang itself might be understood as a kind of hyperspatial event, the collision or fluctuation of higher dimensional spaces. The possibility of parallel universes, entire realms with different physical constants or laws, flows naturally from this picture. Our universe may be just one bubble in a frothing multiverse. Again, he is careful to balance speculation with grounding in equations, pointing out that while these ideas sound wild, they often fall out of the mathematics when taken seriously. One of Kaku's strengths as a writer is his ability to humanize the science with stories of the people behind it. He tells of Einstein's frustrations in his later years, chasing a unified field theory that eluded him. He recounts how young physicists in the 1970s and 80s revived Kaluza-Klein ideas in the context of string theory. He brings in mathematicians who developed the abstract tools necessary to even conceptualize 10-dimensional space. And he does so with a sense of wonder, conveying the audacity of minds willing to imagine realities far beyond ordinary experience. This narrative thread gives the book the feel of an Odyssey, populated not just by equations but by dreamers and visionaries. As the journey progresses, Kaku broadens the focus to consider what higher dimensions mean for human destiny. If wormholes could be engineered, interstellar travel might become feasible. Civilizations advanced enough to manipulate hyperspace might harness energies on a galactic scale. He introduces the Kardashev scale, a classification of civilizations by their energy consumption. Type 1 harnessing planetary energy, Type 2 mastering stellar energy, and Type 3 commanding galactic power. Humanity today is not even at Type 1, but hyperspace physics suggests pathways by which future beings might ascend these stages. For such civilizations, space and time themselves would be malleable resources. At this point, the narrative almost drifts into philosophy. What does it mean if reality is fundamentally higher dimensional? Kaku draws parallels to theology, noting that beings who can move through higher dimensions would appear godlike to us. They could enter locked rooms, see into closed boxes, even pluck us out of our three-dimensional existence as easily as we might lift a flatlander off their page. Concepts like omniscience and omnipotence, he suggests, can be reinterpreted as the natural abilities of higher dimensional intelligences. This does not mean that physics has proven the existence of gods, but it illustrates how science can illuminate old metaphors in new ways. Throughout, Kaku is careful to return to the theme of imagination. Hyperspace is not just a technical theory but a testament to the human mind's ability to picture the unseen. He points out that much of what we now take for granted, relativity, quantum mechanics, curved spacetime, was once considered absurd. Today's speculations about 10 dimensions and parallel universes may sound equally fanciful, but they are part of the same tradition of stretching thought beyond the limits of common sense. Science advances not by clinging to intuition but by expanding it, and hyperspace is the latest frontier in that expansion. Toward the end, Kaku reflects on the broader significance of this journey. Physics has always sought unification, from Newton's law of universal gravitation to Maxwell's electrodynamics to Einstein's relativity. String theory and its higher dimensions represent the next step in that trajectory. Whether or not string theory ultimately proves correct, the pursuit has already enriched mathematics, inspired new experiments, and expanded our sense of what might be possible. Hyperspace serves as both a technical framework and a metaphor for thinking beyond boundaries. It invites us to consider that our universe may be just a sliver of a grander reality, and that understanding it requires us to reimagine not just physics but ourselves. In closing, Kaku suggests that the quest for a theory of everything, a single equation that could summarize all the laws of nature, is as much a philosophical and even spiritual pursuit as it is a scientific one. He muses that such a theory, if written on a single sheet of paper, would encapsulate the beauty of the universe in a form that speaks to both intellect and imagination. For centuries, humans have sought meaning in the stars, weaving myths of gods and creation. Now, with hyperspace, we glimpse a different kind of myth, one rooted in mathematics but no less awe-inspiring. The Odyssey continues, propelled by curiosity and the courage to imagine what lies beyond 3 dimensions. And that's it. Michio Kaku's Hyperspace, a scientific odyssey through parallel universes, time warps, and the 10th dimension. Thanks for listening to Book Nibbles. If you enjoyed this bite-sized book, Don't forget to subscribe for more quick, insightful summaries. See you in the next nibble.